All right. Good morning, everyone. One kind of logistics announcements. Because of tomorrow. Okay. So because of basically some conflicts, Instructor Lake, she had to move her office hours for today. I also have to move my office hours for tomorrow. So I think this is the bigger change. This is only a 30-minute shift in the office hours, just 30 minutes earlier. I hope that doesn't make a big deal. But this is a little bit of a shift here. So just to note, these are the office hours for this week, slightly different than most weeks. Other logistics item, I hope everyone knows this, but the project part 1 is due on Friday. Right? If you have not started with your partner yet, you are well behind. Okay? So I'd recommend you contact your partner if you have not already and get working on that. I know some of you have, but I haven't heard from a lot of you. I assume that's going to dominate a lot of the conversations at office hours this week. Okay. All right, so we left off in Friday's class talking about trying to figure out the dynamics of a speaker, right? So going back to the problem statement, just a reminder, the problem statement was we have a speaker. We parameterize the speaker by having certain spring constants, electrical circuit denotations in terms of resistance, inductance, number of coils, etc., mass. We came up with all these parameters and we said, all right, we want to find the Bode plot, or basically the frequency response, that relates the velocity of the speaker cone. And so velocity of the speaker cone is going to give us an idea of how much pressure waves at the speaker cone face are being compressed, and therefore how well we can hear what's happening from the speaker, to then the voltage signal. Right? And keep in mind, if we're talking about Bode plots, we are talking about harmonic functions. Right? So Bode plot is the most valuable when we're looking at harmonic inputs. We're going to get harmonic outputs of that system. So that's not very well zoomed in, is it? There you go. I hope that helps. Okay, so we started at this problem statement, and then we did a little bit of work before we had to adjourn on Friday's class, where we were looking at breaking down the system into a mechanical system and an electrical system. So again, this class is about systems integration. At least for the first few weeks, we talked about electromechanical machines. So pretty much every system we try and analyze, we're going to have probably a free body diagram to describe the mechanical components of this, and also electrical circuits to describe electrical circuitry inside the system. So we built a free body diagram for the speaker cone mass, which is driven by a magnetic force and then has spring and damping forces on it. And also we looked at the electrical circuit for the speaker. We said that the coil is composed of, can be modeled as an inductor and a resistor. And also we looked at the phenomenon, which is built off of Faraday's law, that we have a back EMF. EMF stands for electromotive force, which creates a voltage across the coil, which is a result of a coil moving through a magnetic field. Right? And so we can then, from the free body diagram, we can get equations of motion for the mechanical system. For the electrical system, we can get equations of motion for the electrical system. And then the last note that we finished off on Friday's class is the realization that these two equations of motion are coupled. Right? So we would say the most dominant factor, the factor you see, I don't know about the most dominant, that's not the right word. The factor you see the most often in the mechanical system equation of motion is U, the velocity of this cone. But you also see that the force is dependent on the current running through this circuit. Right? The current is what's going around this loop. Maybe I'll make this look like a loop to make it be a little bit more obvious. So this is current. Right. Okay. The electrical circuit, what we see most often is I, the current going through the loop, but we also see what drives the entire system, the voltage applied, and we also see the velocity of the cone influences what this back EMF voltage is here. So any questions on that basic idea of mechanical system coupled to an electrical system? So if we are going to eventually get to a Bodhi plot, what do you think we have to do to these equations of motion, which are differential equations? Carson. Exactly, take the Laplace transform. So if we're looking at Bodhi plots, we're talking about having a transfer function. So we need to convert our equations of motion to a transfer function, which means we need to take the Laplace transform. If it's a transfer function, we're assuming that the initial conditions are equal to 0. Right? You go back to lecture 3 and also 3260. That is when your assumptions, when someone says transfer function, you say all initial conditions equal 0. Right? Okay, so we're going to do that. So we're going to take the Laplace transform, assume initially at rest. And so for equation 1, see if we fit this both on, zoom out a little bit. Okay, so equation 1, the Laplace transform of equation 1 all right, so we have mu dot, so this is going to be then m s u of s equals negative b u of s minus k. This is the integral, right? So the integral is 1 over s, or divided by s in the frequency domain. And then we have our current function, which is then going to be the b L I of s. Same thing, Laplace transform for equation 2. We have v of s, Laplace transform of this function, the driving function, minus Ls I of s, minus R I of s, minus BL U of s is equal to 0. All right, so now we have everything. If we look at these two equations, we have everything in terms of u, I, and v, right? So we have 3 variables, 2 equations. So we're not going to be able to solve for anything here, except if we solve for a ratio, right? So ultimately we want u over v, right? So we can solve for this ratio. There are, I think 2 ways in which students do this most commonly. First is just you write, say, the bottom expression in terms of u, then you substitute, or sorry, I guess it would be I, and then you substitute everywhere you see I, you substitute that into the first equation. That's one way to do it. In this example, I think everyone should be very familiar with that. In this example, I'm going to use Kramer's rule. Does everyone use Kramer's rule in 3260? Anyone not see Kramer's rule? Okay, we have one hand kind of go up. Okay, a little bit. Okay, all right. So we'll go through Kramer's rule in this example, and I think this is giving a specific example of Kramer's rule. I think it may. Okay, never mind. My notes do go through a generic example. Okay. So for Kramer's rule, we're first going to get, before we even get to Kramer's rule, we have to get this equation into a form which we can use. And so it's based off of linear algebra. And so linear algebra, if you go back to your linear algebra class, where's my cursor here? There we go. Just a little refresher on linear algebra. I would say basic linear algebra form. Okay, in linear algebra, pretty much every equation you see has this form, right? Ax equals b, right? So A is typically a matrix, x is a vector, b is a vector, right? All right, so we're going to write the equations of motion here in terms of linear algebra form. Okay, so we have 2 equations, 2 unknowns here. V is null. All right, so V is what's driving the system. So if I'm going to write this in terms of then a matrix, which we'll call A vector of unknowns, x, and a vector of knowns. It's going to be A. It's going to be coefficients. These are going to be known, oftentimes. So known coefficients in this x vector, vector of unknowns. And this is going to be our vector of knowns. So our unknowns are I. We do not know I of S. U of S, we do not know the speed, the Laplace transform, the speed of the speaker cone. Right, so those are the unknowns, and we're going to be, we're not actually going to bother solving for I. What's nice about Cramer's rule is we never have to solve for I, it just kind of falls out in the math. But what we're doing is we're going to then convert these equations into this formula. So if we look at the top equation, we see that it is given by m s u of s. If I were to move these terms to the left-hand side to make it a little bit easier, I guess we're going to move everything to such that it's all on one side. We have m s u of s, we have another b u of s, and we have a k 1 over s here. So if we look at this upper right entry, this is going to be composed of ms plus b plus 1 over sk in terms of what's multiplied by u of s. What's multiplied by I of s is negative BL. And if we look at what this is all equal to, it's equal to 0. All right, so this differential equation is not driven by some signal. All right, the second equation, we have terms in that have our coefficients on I. So it'll be LS plus R. And then we have the coefficient on U, which is going to be BL. And this is all driven by V of S. Okay. Any questions on that arrangement right there? So then we have something in the form of AX is equal to B. A little aside on Cramer's rule in case you've never seen it or it's been a while. So Cramer's rule. So we have equations of the form AX is equal to B. And so by this we mean that we can break down this matrix versus vector product into the matrix we can say is composed of individual column vectors. And if we have an n by n matrix, we're going to have n column vectors given by little a sub I. We're going to have then a vector of unknowns. We're of course going to have n of these. And then this is going to equal then a column vector b of size n by 1. So Cramer's rule, I'm not going to go into where this is, how this is derived, because I actually don't know how this comes to being, but it works. So Cramer's rule says that if we want to solve for any of these unknowns, typically if we have this large matrix, AX is B, we would end up invariably solving for a lot of these terms along the way. But what Cramer's rule allows you to do is if we want to say, okay, I'm really interested in x2, I want to know x2, you can use this formula to specifically solve for x2, where we say that the xi unknown is equal to, and I'll give the numerator a second, the denominator is always the determinant of A. Right? So this is the same regardless of what unknown you're solving for. the numerator is how we specify what unknown we're solving for, but we're going to do the determinant, and we're now going to make up a new matrix where we take pretty much A, and then we keep everything the same except for the ith column of A, we're going to replace with the solution vector. So that means if I care about the ith column, I'm going to have A1, A2, all the way up to the ith column. I'm going to replace that with B. And then I'm going to have going all the way up to AN. Okay, so by then evaluating this, we can solve for unknown without having to solve for x1, x2, all the way up to xn along the way. So for a 2 by 2 matrix like this, Cramer's rule is not all that valuable, but we will get up into, say, 3 by 3 matrices in this class, and then that takes a long time to solve for all these unknowns along the way. Cramer's rule is going to be your most efficient way to do that. Yes?
Doesn't it get difficult to take the determinant though?
Of a 3 by 3 matrix? That's not so bad. As you go up, like 4 by 4, 5 by 5, then it gets long. So just, I mean, I think often the follow-up question is that is how large of a matrix would you have to solve in a test? I have asked up to 3 by 3 matrices. 4 by 4 wouldn't really be testing your knowledge of the material, it'd be more testing your bookkeeping. So I've never asked a 4 by 4 matrix on test. Okay, so using this as a kind of a map for our solution here, let me zoom out so we can see everything on the same page. Okay, so we have, okay, so I care about U, right? We're trying to get to a transfer function U over V, right? So I care about what is the second entry in this unknown matrix, right? I care about U of S. So that means when I am composing the numerator here, I'm going to replace the second column with 0 over V of S, or 0 V of S, right, those entries. So that means that U of S is going to be determinant negative BL LS plus R. Drop in the solution vector into the second column. And then determinant of the entire A matrix in the denominator. Okay, I ran myself out of space here. Okay, so reminder, 2 by 2 determinants, right? It's going to be 1, 1 entry times the 2, 2 entry minus 1, 2, well, 1, 2 entry times the 2, 1 entry, right? So that's going to give me negative BL V of S over then B squared L squared minus B squared L squared minus LS plus R MS plus B plus 1 over SK. Okay, you may notice that there's negatives everywhere here, so I can just turn all those to a positive. Right? Okay, I wrote a little larger than I wrote this the first time. Let's cross it out for a second, and then we can expand this out. So if we expand this out, we're going to then get the solution for u of s. And we note that we have, really counting up the number of s's, especially if we have BLS. So one of the simplification, I'm skipping a step, we're going to multiply top and bottom by s to get rid of this 1 over s in the denominator here, and the denominator of the denominator. And so it's going to have then a third order differential equation, a third order transfer function, because we have an s to the 3 term. Okay, so this is all in the denominator. Just writing myself out of row. Yes. Yes. Thanks. Thanks. Okay. Any questions about that? Okay. So then let me add a page here. Okay, so then last thing before we get to actually a Bode plot of this is that we can then, oops, didn't go where I wanted it to go. All right, I'll rearrange these pages after this class to get this in better order. But what we want here is we want this transfer function u over v, right? So I have u on the left-hand side, I have some coefficients and some frequency variables s, and I have v on this side. So I can pretty easily just bring this v over to the left-hand side. We get u over v, right? All right. So then lastly, we're going to make an assumption here. We haven't given coefficients. We've left this all symbolic. But let's assume for a second that u over s, v over s, can be decomposed into a gain. All right. You'll notice in your equation that you have a 0 at the origin in the numerator, right? And then we say we can decompose this into that in a set of real poles. So s over tau 1 plus 1, s over tau 2 plus 1, s over tau 3 plus 1. And then we'll have some sort of assumption that it doesn't really matter what these values are, but these are all not equivalent to each other. We don't have any repeated poles. We just have some sort of ordering of these. Okay, so we're going to say that our transfer function, even though it has all these complicated coefficients, we're not going to go into these coefficients are in this example, but they're something, and we want to understand, all right, what is the general shape of this Bode plot? Right? Yes?
Why did you decompose it into 3 like first order?
Yeah. Yeah. So you're exactly right. So the coefficients could be such. Really, your options are 3 real poles, right? And this is all depending on what your coefficients are. And the other one is 1 real pole and then a pair of complex conjugate poles, right? Those are your only options. So yes, they could be the case that you're suggesting as well. This is just for an illustrative example. Depends on the coefficients. Okay. So anyhow, we have a 0 at the origin. We have then then 3 real poles. So we look at the general shape of, we'll just talk about the magnitude plot here. The notes give the phase as well, but it's not not as important for this discussion. So we have frequency. We're looking at U I omega over V I omega in terms of decibels, magnitude. And if we look at our different contributions here, we have a few things going on. We have one, we have a gain of K. If we assume that K is less than 1, this gives a, let me change the colors up a little bit. Okay, so if we have a gain of K bar, that's this contribution. The 0 at the origin, this causes a positive 20 dB per decade slope in the magnitude at all frequencies, going through the points 10 to the 0 and 0 dB. Okay, so this is this basic function. All right, and then we have a set of real poles, right? So real poles have this basic form. The way we wrote them has that the low frequency gain is 0 dBs, and then we have negative 20 dB per decade slope. Happening at this breakpoint. Tau 1, and then we're going to have another one at tau 2, and then another one at tau 3. Okay, so getting back to your point, if this happened to be the case where we had complex conjugate poles, that would mean that we still have one of these, right? Say, for instance, the one at tau 1, and then we'd have each of these individually contribute negative 20 dB per decade slope, right? The complex conjugate pole after the break is going to have negative 40, and then a resonance peak. We don't have a resonance here. Yes? Ben? No, they're not. So that would be the case of, it's just the form here. So that would be the case, you probably have seen it in another form, which would be S tau plus 1, right? And so in that case, if it's written that way, that would be 1 over tau. Okay, so then adding all these up. Okay, so we have a pervasive change in the magnitude from the gain. We also have this pervasive 20 dB per decade slope. So that means at low frequencies that this magnitude plot is going to go through. I just basically draw this down here, and this is going to go through this point. Okay, so I'm going at positive 20 dB per decade. As soon as I get to that first pole, it's going to go from a slope of positive 20 to 0, right? Because I've taken positive 20 minus 20. Okay, that's the slope of 0. Once I get to the second pole, it's going to now break down at negative 20, and then I get to the third pole, and now it's going to break down at negative 40 dB per decade. So without putting in numbers, this is the general shape of what this frequency response of this speaker will be. Right. So the reason why we're talking about this is I wanted to try and tie this to some general things you may have observed from speakers in your life. Okay, so does anyone in high school or currently have a really, really loud speaker system in your car? Okay, we'll talk about the two people in the middle here. Okay, all right. So when you were terrorizing your neighbors who live two blocks away, what did they hear? They hear the bass or the treble? Bass. Okay. Okay, yeah, so they hear the bass. So your neighbors know this very well. You may not have known because your ears are shot now. But this is basically a general quality of anything that is physical, right? So anything that's physical actually is going to have a trailing off of this magnitude. Where's that? At really high frequencies. So if you look at your speakers are going to, one, they're tuned to a certain frequency, and also as they go through the air, you have a decrease in the magnitude with increasing frequency. This happens in every physical system, whether or not it's mechanical, electrical, etc. If you think about this from the perspective of Newton's first law, I guess, or yeah, first law. Once a moment is in, I forget my Newton's laws. An object in motion wants to stay in motion, right? So if you want to have a mass, right, and you are trying to very quickly move it to the left and to the right by putting a harmonic function into it, right, it's actually going to resist that. So as you go back and forth faster and faster, just the general physics does not allow you to just move a mass back and forth as fast as you want, right? It's going to actually have some sort of diminishing returns. You'll see that basically in the high frequency areas, where all your high frequency content is going to be attenuated by basically the atmosphere. You also have speakers that are tuned to a certain frequency range, right? So your early high frequency, our tweeter speakers are going to be shifted where this peak here, we'll say the peak amplitude, you would select the mass of your cone, so this shifts to the right to higher frequencies, so they actually are efficient in that frequency range. And then your subwoofers, which create the low frequency tones, are going to have larger mass, larger motors, et cetera, and that's all going to be shifted to the left such that it has a high magnitude at the frequency at which they're designed to operate, right? So they can actually achieve low frequency tones or high frequency tones and vice versa. Right? This is just a kind of a general discussion of what the frequency response of these systems looks like, and I think you may have observed that just by knowing a little bit about speakers. If you look at an array of speakers, you'll see small ones are the tweeters, right? Those have low mass. The bigger ones are the subwoofers. Those have a lot of mass associated with them and stronger motors associated with them. Any question about that general idea? Okay. Last comment on that before we get to new content is I wanted to pull up a spec sheet for something because we talked about speakers, but you're probably asking, okay, speakers, how do we use speakers to actually move anything? Or, if I'm going to be a sound engineer, this may be important, but if I actually want to have an integrated system, why would this potentially be important? So I'm going to pull up a spec sheet, which apparently I've pulled up before. Okay, so has anyone heard of a voice coil motor before? Okay, so I brought in the speaker here. Everyone says, okay, I use that to hear things. But you also notice that I could, by controlling the voltage, I can control the position of the speaker, right? And so there are engineering or motion control uses for structures that look exactly like a speaker, and they're called voice coil motors. And so voice coil motors are used for a lot of applications where you want to have really, really fast response times, but maybe you don't want to have the most amount of force, okay? Or maybe you don't care about having a lot of force. Okay, so here's an example of a voice coil motor. It's not the best image here, but you basically have a stage in this region. You notice that you have some sort of coil in this region, and there has to be some sort of permanent magnet in here. This tells you what type of force it can apply. So this is definitely weaker than most motors, 6 pounds. Not incredibly high. That's enough that you could resist it, of course, right? But it gives you some ideas that relate to some of the things we just talked about here. So you have force constant. We didn't explicitly talk about a force constant, but we looked at this equation here, which is what is the force that we get from a motor, right? So the force constant would be BL, right? That is the gain in terms of newtons per amp that you get from this voice coil motor. The other element here it gives you the back EMF constant, right? So this is the back EMF, that's the back EMF term here, And that's in the form of, I guess, volts per meters per second, right? So that is the amount of voltage you get for this coil moving at for a certain velocity, right? Any other things that are interesting? Coil resistance, right? That's R in our electrical circuit that we just looked at. Coil inductance, that's L, right? So a lot of these terms that we just talked about, you can find in some basic spec sheets for a voice coil motor for, again, moving low loads very quickly, if that's what you need for some sort of engineering application. Okay. That's all I have to say about moving, at least linear moving coil transducers. There are, I believe, 2 homework problems on that this week. But next, we're going to get into DC motors. So any questions on linear moving coil transducers? Okay. So we're going to start talking about, this will take probably a few lectures because it's a very important concept or tool, a set of tools that we use in electromechanical machines, and these are motors, right? So these are everywhere. It's everywhere in any type of manufacturing operation, your car, et cetera, all over the place. And so we're going to talk about some of the basic elements of motors. We're going to go through, in particular, the DC brushed motor pretty carefully during this class. So before we get to that, and I have 2 of them up here, we're trying to match up things I draw on the screen with these motors that we're going to pass around. Just going through some really basic ideas of the elements, the major elements in a motor system. Okay, so if we have your standard motor system, it is somehow attached to the earth or some sort of frame that we care about keeping at least the chassis of the motor stationary. All right, so you can see that. I'll pass this around. This has multiple places in which you could bolt this to some sort of frame. Bolt this one, and this one. You see holes, etc. But you can bolt it to some sort of frame here. And then if we look at, from a schematic point of view, what we have going on in one of these motors is that we have what's called the stator. And so the stator is the stationary portion of the motor. Okay, so for the sake of this initial discussion, we're going to assume that the stationary portion of the motor has an electromagnet wound through it that creates a magnetic field. Okay, so there are counterexamples to this. There are permanent magnet stators and there are permanent magnet rotors, which we'll get to in a second. But just for a general introduction to this, we're going to say we have some sort of stator. It has a coil running through it, and we have current into the page on the right-hand side and current out of the page here. So if I look at current into the page on this side, right? That's the B field going this direction. Current out of the page on this side. B field again going from south to north. Or sorry, from south to north of the board. That's not how we denote magnetic fields. So we go from the bottom to the top here. So that means we have a B field from the stator. So that's BS. Going from south to north, or north to south, right? Sorry? Yeah, but so the B field always goes from north to south, right? Okay. All right, so that's the stator, which is then stationary. So this is not going to be a non-rotating B field. This is going to stay, it's going to potentially change in magnitude, but it's not going to rotate. Right? We then have an element on the inside, which we call a rotor. Okay, so this example is going to also have electromagnetic, yes? Yeah, that's why I took a pause. I have an error in the notes. Yeah. Yes.
Previously, did we have north be by the point of the B field, unlike lecture 4?
So it's always going from, so it depends on the context. So it's always going from north to south. Right, so the B field always travels from north to south. So if it's on the outside, all right, I'll have to take a look at this. Yeah, okay. We at least have the arrow going in the right direction. Let me, that's the most important, because that's how we're going to determine torque on this thing. So it depends if you're in the outside, then that of course makes sense, right? But if we're looking actually at the magnetic field through the inside, which is what we care about, let me circle back on that one. All right, that's, you're all confused, I'm confused, we're all confused together. All right, so we'll sort this out. Okay, so anyhow, let's stay with this convention here. We have current out of the page here, right? So that's going to create then, you feel go in this direction, current into the page here, you feel in this direction. X is into the page. Oh, you're right, X is in the page. Thank you. Flip that. Yeah. All right, so then, okay, so for the sake of staying consistent with our argument, which may or may not be true, we have then magnetic field going from north to south, right? And this is going to be the B field of the rotor here. So we have stator, and then we have rotor here. The rotor has some sort of fixed bearings. So this rotor rotates about fixed bearings. All right. And you'll see that when we pass these motors around. All right, so if we look at what we have here, we have it doesn't really matter if these are north or south, but we know that the opposites attract each other, right? So if we look at this rotor is going to have an applied torque on it in this direction to align the south and the north magnetic fields, right? So this torque is going to be in the counterclockwise direction for this configuration. Yes?
So you determine that based off of like this way that the poles attract each other.
Yeah, so we're going to have north and south flipped, but we're flipped, at least we haven't flipped, we're flipping in the same direction. We know it's going to attract. So I'm looking at the torque on the rotor. Now keep in mind there has to be an equal and opposite torque on the stator, but that's fixed to the earth. That's not going to move. So we're not trying to analyze that.
Right, but in terms of like determining the torque, is that like direction of it just based off of like
The south and the north are attracting each other. So that's the kind of the general setup of this. This is what we're describing here, at least, well, it's a little more general, but we have different classifications of motors. We have DC, or direct current machines, and these are ones that are DC, or therefore non-changing amplitude and time, at least not quickly in terms of it's not based on some sort of periodic signal in both stator and rotor. We're going to also be talking about synchronous alternating current machines. We're not going to talk about AC machines in all that much detail, but we will get into a little bit. So this is typically AC in the stator, DC in rotor, or vice versa. And then the last one is going to be asynchronous induction machines. This is AC in both stator and rotor. Okay, and we'll get into what we mean by synchronous, asynchronous when we get to that section. For now, we're going to spend a decent amount of time talking purely about DC motors. Okay. So we have two DC motors up in the front of class. So just to, well, I'll talk about this one first because it's the most general in terms of architecture, and it's also in the best shape, so it actually looks like a motor. The other one is, let's say, worse for wear. Okay. So first off, what we'll observe as you're passing this around, that you may not be able to see it, maybe you can, people in front can probably see it, but you have the rotor. So if I spin this, if you try and look right here, you see these copper contact pads, and those are rotating. And so you'll see that these contact pads are copper, and then they have little divisions in them every so often. Right? So we would call these poles. These have multitude of poles around the diameter of this rotor. So in terms of notes, in terms of observations, so rotor has electrical contact pads. Okay, and then if we were to follow the electrical lines from these contact pads, connect to coils of wire. Okay, so this may be a little bit more difficult to see, but if you kind of follow this, you may be able to tell. But each of these contact pads at the very base then goes, and it then forms a coil from that. Okay, so this is, and you have to kind of look down into the motor to look at what is rotating the stator. You see there are a bunch of coils inside the stator. Some of you may not get it till Wednesday, though. Okay, these coils run through cutouts in laminated steel sheets. This may be a little bit difficult to tell as well. You have to really look in there carefully. Okay, so just like the solenoid that we had in front of class, which we had these laminated steel sheets, I'm only talking about the rotor right now. The ones on the stator are really obvious to see. The one on the rotor is going to be a little bit more difficult. You have to kind of peer in there, but it's running through a bunch of steel as well. Right? So that's very purposeful. We'll talk about why that is later, but just know that this coil is inserting into kind of these cutouts in steel, and they're running through this steel structure. Okay. Observations on the stator. The stator, likewise, has coiled wire. Wrapped around laminated steel sheets. Yeah. All right. And then this may not be too obvious to see when I pass this around, but I'll kind of give a general cross-sectional image of what the stator looks like. But basically, stator, big chunk of metal you see on the outside, big coil you can easily see, rotor, the stuff inside that if you rotate the motor shaft, you'll see the things that are rotating are the rotor, right? So pass it around. Some things might not get that till Wednesday though. Okay, so stator in general is going to look like this in terms of architecture. So of course it could be a circle, not like my oblong, whatever I just drew there, ellipse. If we were looking at a cross section of the stator, it would approximately look like this. So this is going to be steel. All right. And then we're going to have coiled wire. So we have out of the page on the bottom side into the page. Oh, sorry. Out of the page on the top side into the page on the bottom side. That's going to create magnetic flux in this direction. Same thing on this side. More magnetic flux in this direction. All right, so this, given our convention we were talking about before, north to south, flux running from north to south. As a note, what the steel is doing, the steel is directing our flux lines. All right. So we haven't gotten to what the rotor is going to be, but the rotor is going to fill this space in between. It's going to make very small air gaps then between here and here, because we're going to have something magnetic or ferrous connecting all this. Right. So what this structure doing, this is called a salient pole. It's taking the magnetic field generated by the electromagnetic and it's helping direct it into the direction that we want to go to do meaningful work. And so once the rotor fills this space, we're going to have approximately as best possible, a uniform B field going from this direction to this direction. The return, right, it has to make a loop, so the return is always going to then go through the chassis of the structure. So it's going to flux return path here. Okay, so we'll get into more on this in a bit. We're going to start talking about the contactors, and we'll also talk about this motor as well, which is slightly different. The one being passed around has a coils that create the magnetic field. This is actually has a permanent magnet that creates the magnetic field. So the permanent magnets are also wound coil DC motors. We'll talk about this one. This one's in pretty bad shape. You can take a look at what happens to the contactors and brush it up a little bit of time. And you can also see the laminations in the rotor a little better in this one. But I'll have to wait till Wednesday. Any last questions on that last minute? Okay. Oh, yes.
Did we reach the material we're trying to reach for problem number 3 of the homework? It says something that we were going to drive something in class and then we had to use it.
Oh, yeah, yes, we did. All right, I'll move that to after the midterm. Yeah, so if you started on that, that'll show up again. Your efforts are not lost. So. Yeah. Thanks for pointing that out. Yes?
What exact material should we be studying for this first semester next week?
Okay. I haven't thought about that, but basically everything through homework 4. So the homeworks are your guides, essentially. So anything that has been asked in some sort of homework problem, I mean, or I guess I want to say, the class is more expansive than the set of, maybe a dozen homework problems. So, a little more than a dozen, right? So anything that will be spanned by the content of that, so starting the first day of class all the way up to whenever the last homework problem is, anything in between those is fair game. So basically up through moving coil transducers. Okay. See you on Wednesday. Not before.